Sunlight strikes the ocean as a broad spectrum, but seawater immediately begins sorting its colors. You followed one downward beam. Its warmth, brightness, and color would change continuously. The first meters appear radiant because abundant photons still return toward watching eyes. Deeper down, red fades, shadows lengthen, and the remaining world shifts toward blue. This transformation is not a clean staircase of colored zones. Every photon faces absorption, scattering, suspended matter, and an increasingly uncertain path. Some transfer their energy to water molecules and disappear from the visible scene. Others ricochet from particles, changing direction until they escape upward or are absorbed. Only a diminishing fraction continues into the ocean's transparent interior. The mystery is not merely where darkness begins, but how light is dismantled. Its descent links molecular physics near the surface with hunting and concealment far below. Direct measurements confirm rapid spectral change, although coastal and open waters differ greatly. Mainstream interpretation attributes those differences to water itself and materials dissolved or suspended within it. No universal depth marks the final sunlight across every sea season and wavelength. The descent must therefore follow changing probabilities rather than a single boundary. Visible sunlight contains wavelengths perceived as colors when they reach a human eye. Water does not absorb all those wavelengths equally during their passage. Longer visible wavelengths, including red, usually lose intensity much sooner than blue-green light. As you sink through clear open water, familiar warm colors become progressively unavailable. An object reflecting only red light can appear dark because little red illumination remains. Its pigment has not changed, but the spectrum arriving and returning has changed. Blue light penetrates especially well in clear ocean water because absorption is comparatively low. Even blue photons eventually vanish through absorption or are redirected away from their original path. Ultraviolet radiation also changes rapidly and can damage exposed biological molecules near the surface. Water, dissolved organic matter, phytoplankton, bubbles, and mineral particles modify the underwater light field. Coastal runoff can darken water by adding colored dissolved substances and suspended sediment. Phytoplankton pigments selectively absorb wavelengths used for photosynthesis, altering both color and penetration. Clear subtropical gyres often transmit blue light deeper than productive green coastal waters. Scattering explains why light may arrive from many directions instead of one sharp solar beam. Small particles and microscopic organisms increase scattering, producing haze and reducing image contrast. The downward intensity commonly declines approximately exponentially within a layer of similar optical properties. Real oceans violate perfect simplicity because those properties shift with depth, weather, and biology. Waves focus sunlight into moving bright patterns across shallow sand and reef surfaces. Below those flickering lenses, the direct solar beam weakens and diffuse light becomes relatively important. Oceanographers often define a sunlit zone using a small fraction of surface illumination. That operational boundary is useful, but it is not a wall separating day from night. Vision and photosynthesis fail at different thresholds, depending on organisms, wavelength, and background noise. By several hundred meters, daylight is faint. Deeper still, direct sunlight becomes biologically negligible. Spectroradiometers directly record how separate wavelengths decline through the water column. Their profiles reveal local conditions, not an eternal color map for the entire ocean. Optical backscatter sensors estimate particles by measuring light redirected toward an instrument. High backscatter may indicate abundant material, but particle shape and composition complicate interpretation. Laboratory spectroscopy isolates absorption by purified water, pigments, and dissolved substances under controlled conditions. Those results establish mechanisms, while field measurements show how mechanisms combine in turbulent seawater. Underwater cameras provide recognizable scenes, yet exposure settings can exaggerate brightness and restore hidden colors. Artificial lamps transform any deep image by supplying wavelengths that sunlight no longer provides. Therefore, a brightly colored deep animal on video does not prove those colors are naturally visible. The strongest evidence comes from calibrated measurements rather than cinematic appearance alone. Each absorption transfers a tiny energy increment into molecular motion, while their total warms upper water. Scattering changes direction without necessarily removing energy at the first encounter. Repeated scattering lengthens a photon's route and increases its eventual chance of absorption. Pure water sets a basic spectral pattern, but seawater is never optically pure. Seasonal blooms can raise pigment concentrations and shoal the depth of useful sunlight. Storms can suspend sediment, turning a previously clear layer opaque within hours. After particles settle or currents disperse them, transparency can partially return. Clouds reduce incoming light, while a low sun increases the path through atmosphere and water. Sea ice and snow reflect or absorb much illumination before it enters polar water. Cracks and thin ice create luminous corridors beside much darker covered regions. These observations demonstrate that depth alone never determines the underwater light environment. Fluorescence adds another transformation when molecules absorb one wavelength and emit a longer one. Chlorophyll fluorescence can reveal stressed or surplus absorbed energy, but it is not photosynthesis itself. Bioluminescence is different because organisms create light through chemical reactions rather than redirecting sunlight. Its flashes emerge from darkness after the descending solar spectrum has nearly disappeared. At that point, ocean light has changed source as well as intensity. This transition reshapes feeding, migration, camouflage, and communication through the water column. Near the surface, phytoplankton absorb suitable photons, fix carbon, and support marine food webs. When you see greenish water, abundant pigments may be intercepting light that would otherwise travel deeper. Cells adjust pigment systems and photosynthetic activity as illumination changes across hours and depths. Prochlorococcus populations occupy broad sunlit regions with adapted lineages distributed across different light conditions. Their growth modifies particle abundance, which then feeds back upon absorption and scattering. Many zooplankton descend during daylight when visual predators can detect them more easily. They sense declining light, rise toward food after dusk, and reduce exposure during bright hours. That Q-action sequence drives diel vertical migration across enormous volumes of ocean. Counter-illuminating animals produce downward light that can match the dim field arriving from above. A predator looks upward. The silhouette weakens, and the concealed animal gains a survival advantage. Other deep animals flash when disturbed, potentially startling attackers or drawing attention toward the threat. Flash follows contact, spreads through darkness, and may alter which organism becomes the target. Red coloration can function as darkness where red illumination has already been strongly absorbed. However, some animals detect wavelengths differently, so invisibility cannot be assumed from human vision. Bioluminescent signals also face absorption, scattering, and background noise like every other underwater light. Blue-green emissions often travel efficiently through seawater, matching its broad transmission window. Visual systems become highly sensitive, trading sharp daylight performance for detecting scarce deep photons. Human divers experience the same spectral loss, but carry lamps that immediately repaint nearby surfaces. Surface color can suggest pigment abundance, yet it cannot directly reveal the deep light field. Understanding light penetration helps estimate primary production and interpret changes in marine ecosystems. Future investigations need long records that follow optical layers through blooms, storms, and seasonal mixing. Autonomous spectroradiometers could reveal brief events that ship surveys often miss. Improved particle characterization may separate absorption changes from scattering changes more reliably. Models must connect measured surface color with vertical structure without assuming uniform water beneath. Under-ice regions remain difficult because illumination shifts with snow, melt ponds, ridges, and moving cracks. Researchers must also distinguish natural bioluminescence from instrument lights that provoke or overwhelm it. When you return to the original beam, imagine its colors peeling away at unequal rates. Red energy ends near the upper route, while blue continues farther through clearer water. Particles divert some survivors sideways, and absorbing molecules terminate others without a visible trace. At greater depth, a camera may record light that no unaided human eye could detect. Calibration can identify that sensitivity without turning an enhanced image into direct visual experience. The final solar photons do not strike a universal floor. Their probability simply dwindles toward insignificance. Beyond them, living chemistry creates brief signals inside a realm no longer illuminated from above. Future measurements will refine the shifting depths, but the established mechanism is selective attenuation. The beam that entered white ultimately becomes sparse blue, then measurable darkness, then light made by life.